Hello everyone, and welcome back to another remote sensing lecture video. And in this lecture video, I'm going to connect the idea of display, band assignment and display channels to the idea of a spectral profile, and sort of hopefully tie the idea of why things look the way they do when we start to mess with different band assignments, and why you would pick one band assignment over another. So let's talk about this particular band assignment over here, which is tied to this particular image over here. Again, we're working with Landsat, so the wavelength regions are provided in tables in some of the other videos in case you don't remember them off the top of your head, and we'll go through the relevant ones as they come along. But this image is true color, right? And we know that from looking at it, but we also more importantly know that because we have the band assignment of red going to red, green going to green, and blue going to blue, right? And we said that's a special band assignment called true color. And then just to sort of tie this into our spectral profile, what I've done here is I've done some vertical lines to show you which band, right? So you get an idea of which pixel values we're using. So band 2 is blue, band 3 is green, and band 4 is red. And so what I've done is I've created 3 spectral profiles. The blue line down here connects to this blue point, and that's supposed to be water. This gray line here connects down with this gray point here, and that's supposed to be concrete or some sort of urban setting. And this green point connects with this green, or this green line connects with this green point, and that's supposed to be some sort of woody forest green vegetation. And what I want to do is I want to walk through why exactly in true color water looks so dark, urban areas tend to look grayish or white, and then vegetation looks green. Now, I'm going to full disclosure here that some of what I'm talking about is enhanced by the idea of a digital value, or display value, by the idea of a display value, which comes from the contrast stretching, which we're going to talk about in the near future. But for now, you're going to get the general idea and just know that the display values actually sort of enhance this a little bit. So let's talk about water for a second. Right, water in true color is a dark blue or almost a black. And the reason that it's dark blue or black in true color is because water has very low reflectance. Or very low reflectance. Right? In other words, right, the radiance that is detected by the sensor in water is going to be very low in blue, green, and red. So because it has very low reflectance in all 3 bands, it's dark. Okay, so this is the one where talking about display values might make this a little bit clearer. But let's talk about vegetation for a second. So vegetation starts low in the blue, goes up a little bit in the green, and then goes back down in the red. So it's got a shape that looks kind of like this, right? This is what we call the green peak in vegetation. And so this green peak means that of these 3 colors, you're getting very little blue, very little red, and some green. Because you're getting some green, right, it's going to be green in overall color. Because this isn't a lot, right, this value isn't super high, right, it's going to be a dark green. So that's why vegetation appears dark green, because the overall reflectance is still relatively low, but you're getting some contribution of green, especially relative to blue and red. Right? So again, to clarify this, right, for vegetation, right, some contribution of green, little to no red / blue, and because it's some, right, low overall means dark. So let's talk about this urban setting for a second. So urban, right, it's This doesn't really look exactly like a flat line. And again, this is where the idea of the display value really sort of emphasizes this. But again, this is mostly flat. So you're going to get roughly equal contributions of blue, green, and red. And when you get roughly equal contributions, you end up with some shade of gray. And again, we're not talking about display values here. When you talk about display values, these would actually be pretty high in terms of display values. So it's going to be a fairly bright gray or white, which is why it looks that color. I know this was a lot. I know this is a little bit confusing, but again, you're basically just looking at, what is the relative amount related to the spectral profile is going to tell you what the relative color is going to be. If it's a flat line, it's going to be some shade of gray. If it's relatively high, it's going to be closer to white. If it's relatively low, it's going to be closer to dark gray or black. And if you see peaks like you do with vegetation, that's going to be the predominant color. Okay, hopefully that made sense. What I want to do now is I want to go back up a step, and I want to talk about this one right here. So this example, right, we have band 5, which is the NIR band. So this is our red. We have green being driven by band 4, which is our red here. And we have our blue band right here being driven by green. So this is our blue band here. Okay. So I want to talk about vegetation for a second. Why does vegetation look so red? Or in some cases, a little bit purple? Well, it does that, right? Because we've now replaced, right, red, right, this is now NIR, right? This is now red, and this is now green. And if you remember, we had a special name for this, and it was called color infrared. This is a color infrared image. Okay. And again, why does vegetation look red? Well, if you look at the spectral profile, it makes perfect sense, right? Because the red is dominating, right? It's dominating the spectral profile. So band 5, which is near infrared, has very high reflectance, or very high pixel value, I should say. Because it has a very high pixel value, right? And we're saying the near infrared is driving the red band assignment, right? Vegetation is going to be very bright red. Because again, right, green, which is being driven by the red wavelengths, is relatively low, and blue, which is being driven by the green wavelengths, is relatively low. And you'll notice that in some spots, right, it appears kind of almost more purpley, and that's because the near-infrared reflection actually goes down a little bit, and the blue reflection actually goes up a little bit in some of these areas where you have differences in the quality of the vegetation. So again, why does vegetation appear red in a near-infrared image? Because vegetation has high reflectance in the near-infrared, and that is dominating the red display channel. And that red display channel is dominating what's being displayed. Right? High in the red, low in the green, low in the blue means that you're going to be predominantly red, and that red display channel is being driven by the NIR reflectant or pixel value. Hopefully that makes sense. So I want to let's solidify that. Right, vegetation is red in false color because vegetation has high NIR reflectance and NIR is driving the red display channel. And when I say false color here, what I mean is color infrared. Hopefully that made sense. I want to look at one more example. I want to look at this example. So in this example, right, this is a false color. It's not color infrared, it's false color, but it is still false color. And in this case, vegetation looks green again. So you might be thinking this might be true color if you were looking at the vegetation. But if you look at the band assignment, right, band 6 now, this is band 6, band 5, and band 4. Okay, so what have we done here? We've now moved, right, NIR We've now moved NIR into the green. We've moved red into blue. I'm making a mess of that. Let's start over with that. What have we done? Well, we've moved the red display channel is now being driven by SWIR. Right, because band 6, right, this is shortwave infrared. Right, the green band, or the green display channel is now being driven by NIR. And our blue display channel is now being driven by red, which again is why this is false color. But vegetation still looks green. Well, why does vegetation still look green? Right? You're thinking, oh, it shouldn't, right? It should only look green in natural true color. Why does it look green here? Well, let's take a look at the spectral profile. Right? The spectral profile, we have high reflectance. Right? We have high reflectance in band 5. We have moderately high reflectance in band 6. And we have low reflectance in band 4. So if band 5, right, this near infrared is driving green, you're likely to have a lot more green color, right? Band 6 is kind of high, right? So you're going to add a little bit of red into that. So that's why you have green, but it's tinted maybe a little bit yellow, because you have NIR is driving green, so green's going to be the predominant color. And then you have red being driven by the shortwave infrared, which is also kind of high. So that's why you have some areas where it's tinged a little bit more yellow, but it's still predominantly green. Hopefully this makes sense. I know there's a lot here. But again, right? High band 5, right? This is the green display channel. Right? And so basically for vegetation, right? Anywhere that you move the NIR band to, the vegetation will be predominantly that color, right? So if we move the NIR, if we use the display channel blue, right, trees would turn blue. So hopefully that makes sense. And again, as always, please reach out. Thank you.